Hi everyone! I'm going to talk today a little about tense logic and relativity theory. Well, maybe you already have heard about some temporal paradoxes of special relativity like time dilatation or the twin paradox. And it's kind of known that the idea of time in relativity theory can be a little different from the idea of time we usually have when we talk about it. And this can be very interesting to be studied with a tense logic. I'm going to explain these questions a bit more, but first I'm going to introduce myself. My name is Angel. I am a doctoral student at the Federal University of Santa Catarina, which is in south of Brazil, in the city of Florianopolis. Well, we have a great logical group here working on modal logics, set theory, paraconsistency, and quantum mechanics, and also logical structure of physical theories in general. And my area, it's, as I said, is tense logic, and I also like physics, so I am studying tense logic for relativity theory. And so I am interested in general, I'm interested in tense logic, the time aspects of relativity theory, and philosophy of time in general. I took some classes in physics, but my background is mostly in philosophy. I studied philosophy in undergrad, and it was when I first got studying tense logic, because my supervisor back then, he was studying a tense logical system to try to formalize some verbal tenses in Portuguese. And I found that very interesting, so I started studying it. And I also like the fact that tense logic kind of has to deal with some idea of time. And I thought that it could be very nice if we have a tense logic for the idea of time of special relativity theory. So I started studying these questions, and I carried this research in master's degree, and I'm now continuing this research in doctorate. So I hope I can get some of you interested in tense logic or temporal aspects of physics in general. Before I start, I'd like to thank Maria and Gabriele for the invitation to talk here in Lógica MX, and I'm going to share my screen with some slides, and let's get started. Okay, so I'm going to split this presentation in three parts. Well, first I'm going to introduce tense logic if you're not familiar with it. I'm going to introduce the basics of language and semantics, so we can understand a little how tense logic deals with different ideas of time and how we can introduce the idea of special relativity in a tense logic. Next, I'm going to talk about special theory of relativity, only the time aspects of the theory. And we actually have three theories of relativity, the classical one, the special one, and the general relativity theory. I'm only going to talk about the special theory. And finally, I'm going to show a little the link between these both areas, tense logic and relativity, and try to understand how we can make a tense logical system using the idea of time of special relativity, if it's possible, or what problems we can face. So let's start with basics of tense logic. We can have many different approaches to logic. We can have a more mathematical approach and use logic to try to study the foundations of mathematics, or we can use logic to study theorems about logic, like math logic. But I think most of the logic courses start with the use of logic to study arguments, like this one. We can check if the premises is true, if the premises are true, and if the conclusion is also true. And we can use the logic operators to formalize this and study it using inference rules or truth table. So let's check this argument here and see what we have. It says, if Mary is a teacher, then she works in a school. Mary was a teacher, therefore Mary works in a school. Well, we would not say that this is a valid form of argument. It says, if Mary is a teacher now, notice that the verb is in the present, Mary is a teacher, then she works in a school. But the second sentence says that Mary was a teacher. We cannot infer that she is working in a school right now. She maybe got retired, she maybe has changed her job. From these two premises, we cannot say that the conclusion is true. She may be still working in school, but this is not guaranteed by the premises. So we would say that this is an invalid form of argument. And We can check this using classical propositional logic. We don't need first order logic. We don't have any quantification here. So we can use P to represent Mary is a teacher, and we can use Q to represent Mary works in the school. So when formalizing, we would have something like this, which is a valid form of arguments. You can check that this is really the case using a truth table or maybe a rule of inference like modus ponens, and you'll see that this is a valid form of argument. But we thought at the beginning that this was an invalid form of argument. The conclusion is not guaranteed by the premises. So what is wrong here? It's, as you see, we are using the letter P to represent Mary is a teacher. But in the second sentence, we have Mary was a teacher. But this is being represented by the same letter here, letter P. As you see in the first premise, we have the sentence Mary is a teacher and Mary was a teacher using the same letter, and you consequently have a valid form of argument. Okay, so you can try to fix this, maybe choosing another letter for the second sentence. Let's say we choose the letter R, and we would have something like, if Mary is a teacher, then she works in a school. Mary was a teacher, therefore Mary works in a school. Well, this is not a very good solution, because by choosing a different letter to represent these sentences here, we are kind of saying that it's a completely different sentence, but it's actually not. The only difference between the sentences is that in the first one, we have the verb in the present, in this one, the verb is in the past. So we need a better solution, and tense logic can deal with this by introducing new logical operators that can represent the verbal tense of the sentences. So let's see how it works. We're going to use these 4 basic operators here that were introduced by Arthur Pryor, and we have letter F that can be read as it will be the case that. We also have letter P that can be read as it was the case that, and we also can define another 2 operators that can be read as it is always going to be the case that, and it has always been the case that. Using these 4 operators, you can formalize many different things, many different verbal tenses. So let's see how we can formalize the argument we've just seen. If Mary is a teacher, then she works in a school. Notice now that we are using this operator here to represent the past, so we can read this as it was the case that Mary is a teacher, therefore Mary works in a school. So using the sentences in the present, but now we have this past, this letter P to represent the past tense of the sentences. But the question now is it a valid form of argument or not? Can we use a truth table to analyze this? Can we use modus ponens as we've done in the previous slide? How can we check if this is a valid form of argument? When we are talking about the classical logical connectives, like this implication here, we can check the true value of the sentence like this one by checking the true value of the components of the sentence. Like, if this is true, let's say it's true. If this is false, I know that this implication is going to be false. But how about this tense operator P here? If the sentence Mary is a teacher is true now, how do I know if the sentence with the operator is going to be true or false? If I say that this is true, then I try to use a truth table to say that this is false. It's not going to work very well, because there is nothing that guarantees me that if Mary is a teacher now, then it was false that she was a teacher in the past. And also, if I say that this is true, I have nothing to guarantee me that the past form of this formula is going to be true as well. So we need a better way to define the semantics for these tense operators, because they are not going to work in the same way as in classical logic semantics. We're going to have to work with a structure or an idea of time to be able to define the semantics of these new operators. Let's see how. So we have a representation of a timeline here, and we can understand each part of this line as being an instant of time. Here we have, I think, 15 instants, and we can understand this one as being the present, And we can understand all of the instance behind it as being the past and all of this instance here as being future. So the sentence, Mary was a teacher, is true if this preposition alone happens, or if this preposition alone is true anytime in the past. So in this case, we have Mary was a teacher here in the present, and we have Mary is a teacher here in the past. That makes the sentence here true. If we had the future case, like it's going to be the case that Mary is a teacher, or it will be the case that Mary is a teacher, this sentence would be true if Mary is a teacher happens somewhere in the future. This is a way to visualize this, but we can also define this formally. If you have any contact with modal logic, it's very similar to the possible world semantics, and the only difference is that instead of having possible worlds, we're going to have instance of time in our set. Let's check this formally. So to define a semantics for tense logic, we need to define a frame. A frame is a pair with a non-empty set and this binary relation that we call the precedence relation. And in the set, we can have as many elements we want, and we can understand these elements as being instance of time. So we can have instance t prime, instance t double prime, and so on. We can have as many elements we want, and we also can define the precedence relation the way we want. We can say that t, it precedes t prime. It can also be read as t is in the past of t prime, or t prime is in the future of t. So we can have an infinite elements if you want. We can have maybe a first element or maybe not. So we can choose the set, the frame, the way we want. And this is going to influence what is true and what is false in our tense logic. If we choose a different frame, we're going to have a different tense logic. And for the definition of the operators, we have the definition of evaluation is a function assigning each variable p a true value, true or false, in an instant of time. So the difference here is that instead of saying that the sentences are true or false, we're going to say that they are true or false in an instant of time specifically. So we can define the operators f and p as fp is true in the instant of time t1, if and only if there is any instant of time that is in the future of t1, and this variable p is true in this instant of time. So in the same way, we can say that this operator here, it's going to be true in this instance of time if there exists any instance of time in the past of t1, and this variable p is true in this instance of time in the past of t1. We can, in the same way, define the g operator that says it's always going to be the case that p in the instant t, if and only if for all of the instants in the future of t, p is true. So the same thing happens for the h operator here. It has always been the case that p is going to be true in this instant t, if and only if for all the instants in the past of t, p is true. As I said, we can choose any set of instants for our frame. We can have one set with just one instant of time. We can have with 2 instances, 3 instances, or infinite instance of time. As long as it is a non-empty set, we can have a frame as the way we want. And we can also specify how these instances are ordered exactly the way we want. So let's say, for example, let me clear here. Let's say, let me choose here. Okay. I want to have a temporal logic that the timeline or the instants in the timeline are organized in a transitive way. So let's say for every 3 instants, t, t prime, and t double prime, I want that if t precedes t prime and t prime precedes t double prime, I want that t also precedes t double prime. It seems reasonable that time kind of have this order, right? When we think about time. So if I want this order, I need to choose a set of elements t and say I have 3 instances and they are organized in a transitive way. I can specify even more. Let's say I want to have a frame, or I want a tense logic with infinite instance of time, and I want it to be linear. I don't want like branches of possible timelines like this. So I want here to be the present, and I want it to be linear. I can also specify this in my frame. I can specify even more if I want to temporal logic with that captures an idea of time. The time has no beginning, so there is no first element here, and time maybe has no end as well, so there is no last element here too. I can specify this in my frame, and what we're talking about so far is how to define a temporal logic or a tense logic using a semantical approach. But we can also maybe be interested in the syntax purely of the systems. So if I can introduce a temporal logic specifying a frame or a set of instances and specifying how they are ordered, but I can also introduce a temporal logic choosing just a set of axioms and some rules of inference. So if I want to say that my temporal logic is transitive, I may have a set of axioms that represents or can capture the idea that the instances are organized in a transitive way. So if I choose to have a temporal logic that is transitive, I may have this formula here that as an axiom. How can I check that this formula is actually true or it's actually valid in a transitive frame? We can, for example, let me clear here first. Okay, so I want to make a tense logic where the instants of time are in a transitive order. And I want to choose this formula here to be one of the axioms of my system. How do I know that this formula actually works for a transitive order of elements? Well, we can do this by assuming that this formula is not true, is actually false in an instant of time. Let's say that is going to be the case. Well, it will be the case that P implies it will be the case that P it's false in this instance of time, so it's equals 0. If this is false, what do we have here? We have an implication, and for this to be false, we need this first element here, first part of the implication, to be in the instance A. We need this to be true, right? And we need this part to be false in the instance T. Well, for this guy here to be true, we need that, as we've seen, the definition for the future operator, we need what is in front here, we need this to be true in an instant of time that is in the future of T. So let's say we have T prime that is in the future of T, and in this instant here, we need this guy here to be true. So let's write this here. Well, if this is true, again, we have a future operator. So for this to be true in the instant T prime, we need to have another instant of time, let's say T double prime. And we need that this guy here to be true in T double prime. So let's write this here. We are assuming that our order of the instants are transitive. So if we have this, T precedes T prime and T prime precedes T double prime, we necessarily have that T precedes T double prime. So again, what do we have that we haven't analyzed yet is this. It will be the case that P, it's false in T. For this to be false, we need to have P being false in all of the instants in the future of T, and that includes T double prime. But we have just seen that P is true in T double prime, and now we just seen that P is false in T prime, in T double prime. So if we assume that this formula here is false in a transitive frame, we get to a contradiction. So it must be true. So we can choose this as an axiom of a system if we want to introduce a system in a syntactical way. So to resume, we can introduce a system in a semantical way, and we do this by choosing a frame. By choosing a frame, we need to choose a set of axioms, a set of instances, and we can have any instance we want in this set. Remember the set T, we need to choose, well, as many instances we want, as long as it's not empty, and we also need to specify the precedence order. And this is a semantical way to introduce a system, but we can also introduce a system in a syntactical way. So we do this by choosing a set of axioms to represent or to be equivalent of the semantical way we introduced. So I can say that my set of instance, it's linear, so I would choose one axiom to represent this. I can say that my set of instance has no beginning, so has no first instance, and I can choose another axiom to represent this. And the question now is how, let me clear this first, just a moment. So the question now is, how would it be a frame and a set of axioms that captures the idea of time of relativity theory? And this idea can be a little different from what we were seeing so far. And we need a way to understand how the instants of time are organized in the idea of time of relativity theory. So we can choose what set of axioms and rules of inference we can have in our tense logic. So how can we make a tense logic that captures the idea of time of relativity? But first, to understand this, we need to understand where this representation comes from. So let's check a little about special relativity now. Okay, so what is a relativity theory? Well, a relativity theory is a theory that studies how an event is seen or how an event is described by different observers. And it has some principles. The first one is that the laws of physics have the same form in all inertial systems of reference. What does it mean? Well, first, what is the inertial system of reference? An inertial system of reference is one that the sum of the forces acting on the system is equal to 0. So, well, let's say, for example, we have this pen, and we want to know if this pen is a system, inertial system of reference. I don't know if you can see here in the camera. Let me open my camera to show you better. Okay, so we have this pen here. And I want to know if it's an inertial system of reference. Well, is there any forces acting on this pen? Actually, we have the gravity force in this direction, but we also have my hand here that is also a force in the opposite direction. If we sum both of these forces, the sum will be equal to 0, which means if I am an inertial system of reference, and this pen is also an inertial system of reference, when I look at it, I'm going to see it stopped or moving in a constant velocity. So I'm looking to this pen and I see that it is stopped, it's not moving. When I compare it to myself, it's not moving, so I can consider this inertial system of reference. It could be moving. Let's say I apply one force here, and let's say it's moving in a constant velocity now. Well, if it's moving in a constant velocity, I'm going to have the sum of the forces also equal 0, because I'm applying a force here, but I also have the force with my hand in the opposite direction. If I sum both, it will be equal to 0, and it's going to be in a constant velocity. So to sum up, to resume, an inertial system of reference, it's the one that is not moving or moving in a constant velocity when we look from another system, inertial system of reference. It's a way to visualize this, but formally it's any system that the sum of the forces is equal to 0. and we're going to use concepts a lot. So let me share the slides again. And the second postulate of relativity theory is that the speed of light has the same value, which is 300,000 kilometers per second, in all inertial systems of reference. Now, how do we go from here, two simple postulates, to having trouble with the idea of time in relativity? I said that relativity theory describes how an event is seen or described by different observers. And what is an event? An event can be an explosion, can be the movement of an object, and we can describe an event or a path of a moving object by choosing a couple of axes and say how many centimeters or how many seconds did it take to this object go from A to B. So let's say one example. I'm going to choose the vertical axis to be the time axis, so I'm going to write letter T here. And remember, we were using a lot of letter T's to represent instants of time. Now, let's forget a little what we've seen in tense logic to not make confusion with the letters here. We're using T to represent the time axis. And I'm going to write letter X here to represent the space axis. And let's say I have here 1 second, 2 seconds, and 3 seconds. And here I have, here is in seconds, and here, let's say you have centimeters. And I'm going to write 1 centimeter, 2 centimeters, 3, 4, and so on. And let's say we have an object that in t equals 0, it's right here. And then it moves to here, and then maybe in t equal 2, it's here. And let's say then it comes back here. So I can draw the path of this object by doing like this. And that's a way to describe the movement of an object. So we're going to use a lot of graphics to understand how objects and events are happening in space-time in relativity theory. But the difference now is, well, let me clean yours first. Okay, so I'm going to choose kilometers here instead of centimeters or meters to be easier to write. And instead of writing 1, 2 kilometers, 3 kilometers, I'm going to write 300,000 here in the first here. And here I'm going to choose to write 2 times 300,000. So I'm going to write here. Now I'm going to write 3 times 300,000. Okay, you can see now where these numbers come from. Well, 300,000 kilometers per second is the velocity of light. So why are we choosing this? A graphic or a diagram with this division here with the t in the vertical axis and the x or the space in the horizontal axis, and with this 300,000 kilometers, 600,000 kilometers, is known as a Minkowski graph or Minkowski diagram, or also Minkowski spacetime. And it's very useful to understand some aspects of the postulates we've just seen about the velocity of light. So let's say we have an observer or an inertial frame right here. Let me draw him. Let's say I am right here. Well, that's me. And I'm right here in the beginning of this graph, or in the region of this graph in t equals 0. And I turn on a light. Well, how would be the path of the photon in this graph if I turn on a light right here? Well, the light, we know the velocity of light is the same for all observers, is always the same value. So in the first second, the light is going to be this first photon I turn on is going to be right here in the first second. In the second, the light will be right here, right? So in the third second, the light will be already here. So the photon will be here. If I want to draw the path of the light in this graph, it's going to be something like this. So this is the path of the light sign in this graph. As you can see, it has a 45-degree angle between both axes. And let's try to get a bit more familiar with this kind of graphic and try to understand what would be my path in this graph. Obviously, I cannot walk as fast as a light sign, but let's say I stay there and I don't move for 3 seconds. Well, let's change the color here. Let's say in this t equals 0, I'm here in the origin of the graphic, and the t equal 1, I'm still in the same position, so I didn't move, I'm still here. In t equal 2, I'm still in the same position in x equals 0, and in t equal 3, I'm still in the same position. So my path in this graph would be something like this, right? Now, if we were considering a bigger graphic with the negative side of the x-axis, we would see that the path of light would also go to the negative way, also with 45 angle between the two axes. Let's see this better in another graph. So if we have a graph with also the negative side of x-axis, and I am here right in the region of this graph, and I turn on a light, the light sign, or the photons of this light, would be, after 1 second, would be here in the kilometer 300,000, and also would be here in the negative direction. After 2 seconds, the light sign would be here and also here. After 3 seconds, we'd have this. And as you can see, if we were talking about a 4-dimensional or a 3-dimensional space, the trajectory of light would be very similar to a cone. So this is what is called a light cone. A light cone, it kind of defines what is in the future and what is in the past of an observer. If I'm here in the region of this graph, and this light cone describes that everything that is inside it, so in this region here, inside light cone, is in my future. And everything that is outside the light cone, so this area here, is not related, is not temporally related to me. So let's say there is someone hanging right here outside my light cone, and I want to communicate with this person. I'm still here in the origin of the graph, and I want to communicate with this guy here. Well, any message I could send, it's limited by the speed of light. So if I want to reach this person here, I would have to send a message that after 1 second, this message would be here in 600,000 kilometers. But that's impossible, because if it's limited to the velocity of light, after 1 second, my message would still be here and not here. So anything outside the light cone, it's not temporally related, because it can have a casual relation with anything outside my light cone. Because I cannot communicate, I cannot send any message, I cannot reach anything outside the light cone because of the speed of light is limited. So let's clean this, and let's go back to this slide here. I hope we're getting a bit more familiar with this graph by now. So now let's imagine that in t equals 0, I have a friend in a spaceship, and she is traveling at half of speed of light, and right here she passes by me. And how would be her path in this graph? Well, if she's traveling at half the speed of light, after 1 second she would be around here, and after 2 seconds she would be like here, and after 3 seconds she would be another half of speed of light, so around here. And we can plot the graph of her path. So it would be something like this. Now we want to compare my frame of reference with her frame of reference, which is moving in half of speed of light comparing to me. So to make things more easy to visualize, let's say we have another spaceship here, 300,000 kilometers in front of me, also traveling with half of speed of light. So after 1 second, this spaceship should be around here. Well, after 1 second, traveling at half of speed of light, this spaceship will be around here. And after 2 seconds, well, with half of speed of light, this spaceship would be around here. After 3 seconds, it would be around here. So we can plot the graph of this spaceship as well. So let's do this. Now let's draw another couple of spaceships traveling at the same velocity, half of speed of light. And let's say the third spaceship, it's in it starts from here in 600,000 kilometers, and after 1 second, if it's traveling at half the speed of light, it was going to be around here, and after 2 seconds, it's going to be around here. After 3 seconds, around here. And the last spaceship, it starts from 900 kilometers in front of me, and after 1 second, it's half the speed of light, so after 1 second, it's going to be here, after 2 seconds, it's going to be here. And let's plot the graph of these other two spaceships. So what we have here is that I have a friend passing by me in t equals 0, and she's right here, and I also have 3 other spaceships traveling at the same velocity, half of the speed of light, and they start their journey in 300 kilometers, and the second spaceship starts its journey here, and the third spaceship starts traveling from here. So how can we compare my frame of reference with the frame of reference of my friend, which started right from here? We can plot her graph on top of mine to try to do this comparing. Remember I said before that we started our reference frame here in the origin of the graph, and if I stay stationary after 1 second, I would be here. After 2 seconds, I would be right here, so still in x equals 0. After 3 seconds, I'll be here, and I can draw my path in my reference frame, and it would be equivalent to this t-axis. So my path, if I'm stationary, it's something like this. Well, all of the inertial frames are equivalent, so my friend that passes by me, she can consider herself stationary as well. So her frame, from her frame of reference, the t-axis would be this one, exactly this one. Well, let me change the color. So from her system of reference, this would be the t-axis, the time axis. And down here, she would have the x-axis. I'm going to draw in blue, so we can understand that we have in black, it's my system of reference, and in blue, it's her system of reference. So we have 4 spaceships traveling at half the speed of light when I'm seeing this from my system of reference. But from the system of reference of my friend here, let's call her S prime, and let's call my frame of reference just S. And from the S prime frame of reference, it's like these other 3 spaceships here is like they're stationary because the distance between them does not change. If we take any point in this graphic, they're not going to have the same value for me and for my friend in her reference frame. So let's say, for example, I choose here, the x value in my system of reference can be found by going parallel to my t-axis. So the value of this point in my graph is going to be 600 kilometers, 600,000 kilometers. But for my friend, this point is not 600,000 kilometers in front of her. Notice that I draw a point right on the path of the second spaceship right here. And I know this spaceship, it's 300 kilometers in front of her. So in her point of view, this point is only 300 kilometers in front of her right here. So the x prime would be equal to 300,000 kilometers. Well, what's the problem here? Well, the problem is that imagine that my friend, when in the exact moment that she passes by me in t equals 0, she sent a light sign, she sent a photon, and we want to compare how the path of this photon is going to be. So let's change the color here. Let's say in t equals 0, she sent a photon, and this photon, of course, is going to travel by the speed of light, so 300 kilometers per second. So after 1 second, this photon is going to be 300 kilometers in front of her, so it's going to be here. After 2 seconds, this photon is going to be 600 kilometers in front of her, so the photon is going to be here. After 3 seconds, this photon is going to be another 300 kilometers in front of her, so the photon is going to be, well, here. Now let's draw the path of this photon from her reference frame, which is going to be something like this. And it's a little messy here, but try to draw this and try to understand what's happening here. This yellow first path here is the photon that I sent from my point of view. Well, it travels 300 kilometers after 1 second and another 300 kilometers after another second. So this is the path of the light in my point of view. But from her point of view, well, the path of light is a little different. So when I look to the photon that he sent, it's like it's traveling faster than the speed of light. Because after 1 second, I'm going to see the photon right here. After 2 seconds, I'm going to see the photon right here. So that's a way faster than the 300 kilometers per second that it should be. So if we consider a normal spacetime or a Newtonian spacetime, we have problems like this, that the speed of light may not be the same for all observers, but that's one postulate of the theory of relativity. We need the speed of light to be the same for all observers, so we need to change some graphics. So to keep the postulate that the speed of light is the same for all observers, we're going to have to change some things. Especially, we're going to have to assume that space and time is not exactly the same for all observers. Well, let's see how. So here is another way to represent my reference frame and the reference frame of my friend traveling half of speed of light. And as you can see, the time axis and the space axis are not exactly in the same place. Why is that? So let's check. Let's say, for example, we have a point in our graph that it's right here. If I want to know the value of the axis, the x-axis or the space axis in my reference frame, I go parallel to the time axis. So I go here in the vertical and I can find the value of the space, which is 300 kilometers in this case. And if I go parallel to the horizontal axis, I can find the value of the time axis, which is t equal 1. If I want to know where this point is in the frame of reference of my friend, I need to go parallel to the t-axis, exactly as I've done, but now I go parallel to the t-axis and I can find around here the value of the x. As well, if I want to know the value of time, I need to go parallel to the x-axis and I can find the value of t around here. So this point here has 300 kilometers in my reference frame and 1 second. So notice that this is the value of the speed of light. So this is exactly 1 point on my light cone. And I need these values to be the same for my friend. So here I need to have also x equal 300,000. And here I need to have t, trying to make a difference, I need to have t equal 1 second. Also here I have 600,000 kilometers in my reference frame, and in the reference frame of my friend I also need, let's try to go parallel to the t-axis and draw this a little better. I go parallel to the t-axis and I find around here also have to be 600 kilometers. And I can go parallel to the x-axis and I can find the value of the time in my friend's reference frame, which also have to be equal to. So notice that we can keep the speed of light as being the same for all observers, as being the same for me and for my friend. But to do this, the time and the space axis are not going to be the same. Let's clear this to try to understand a little better. So in my reference frame, any points I choose on this line here in t equals 0, I can also say that all of these events are in my present because they are in t equal 0. And any point I choose on the x-axis of my friend reference frame, it's always going to be t equal 0, but her t equals 0. Let's call it t prime equals 0. So I say that this event happening right here is in my present, but it's not in the present of my friend's reference frame. But this point here, now it's in her present because it's in her t prime equal 0. So I can say that all of the events happening in her present are actually happening in my future. So as you can see, for example, this event right here, it's happening in her t prime equal 0, but it's happening in my t equal 1. So for me, this event is happening in 1 second, and for her, this event is happening in the second 0, so it's happening in the present. We will try to get a bit more familiar with these representations, but just have in mind that to keep the postulate that the velocity of light is the same for all observers, and that's an important postulate of the special theory of relativity, the representations, the graphic of these both systems, they are not going to be in the same position. So we can keep the postulate that the light is the same velocity for everyone. Here we have the coordinates or the diagram of my friend's frame of reference only. Let's try to understand this a little better. If I want to find any points in this diagram, let's say I want to know the t value of this point here, I go parallel to the x-axis, so I can find this being right here in t equal 1. Let's change the color of this pen. If I want to know the value of the x in this point here, I go parallel to the t-axis, so I can find around here, which would be 300 kilometers, as we've seen, 300,000 kilometers. If I want to know, let's say that this point here, I want to know the value of the time of this point, I go parallel to the x-axis, so I can find the value of t, which would be around here in t equal 2. And I also can go parallel to the t prime axis to find the value of the x prime. I hope you got the idea of finding points and events in another frame of reference, but we are interested only in the time aspects of the theory, so let's use the graphic only with the lines of the time. Let's say I have a point or an event happening right here, and I want to know the value of t, the value of time in this event. I go parallel to the x-axis, so I can find the value of t being right here in t equal 0. Let's say I have another point or another event happening right here, and I want to know the time of this event in this reference frame. So I go parallel to the axis here, and I can find that also t is equal 0. Let's say I have another event happening here, and as you can see, all of the events on this x line, on this x-axis x line, is going to be all of them in t equal 0. So we can say that all of these events are happening in the present of this reference frame. Let's say I have another event happening right here, and I want to know the value of t. I go parallel to the x-axis, so I already draw the lines to make it easier. So the value of t would be t equal 1 second. And if I have another event happening right here, I want to know the value of the time of this event. I go parallel to this axis here, and I find that also this event is happening in t equal 1. So all of the events on this line here are happening in t equal 1. The same for this in t equal 2, 3, and 4. All of the events happening on this line are in t equal 2, or all of the events happening here are in t equal 3. So these lines make it easier to see when something is in the past or something is in the future. I would say that this event is in the future of this one, right? Because this one is happening in the present, or t equal 0, and this one is happening in t equal 1. So this one here is in the future of this one. But in this reference frame, different if we compare two reference frames, my friend's reference frame and my one. So let's plot both graphics together again and try to see how events can be seen from my frame of reference and from her frame of reference. Here we have both graphics plotted together, and let's choose some events on these graphics. Let's say I have an event A. I'm going to call this event A. An event can be anything, can be an explosion, can be something happening. We often use explosions because it's easy to visualize. So let's say we have an event A happening here. And I want to know the value of this event, the time that this event is happening in my reference frame, which is the lines in black. Well, I go parallel to the x-axis, so I can see that this event in my reference frame is happening in t equal 1, right here. So in my reference frame, this event is happening t equal 1. But I want to know now in my friend's reference frame. Well, I go parallel to the x-axis. Let's draw. Here is the x-axis. Here is the t. As we okay. It's better call this let's t prime to make different from my reference frame. I can call this t x prime to be different as well. And here is the x-axis. So I want to know where this event is happening in my friend's reference frame. I go parallel to the x-axis. So I see that this event is not actually happening t equal 1, but it's happening t equal 0 for her. So this event is happening in her present, but not in my present. For me, this event is happening in t equal 1. Let's say I have another event right here. I'm going to call it B. And for me, as you can see again, for me, this event is happening in t equal 2. But for my friend, this event is still happening in the present, in t equals 0. We can find this by going parallel to this line here, and we can see that for her, the event is happening in t equals 0. Let's write one last event here to understand this. Let's call it event C. And this event is happening in my t equal 3, right? And for her, this event, it's happening right here in t equal 2. Okay. So let's try to compare the three of them. Well, this event A and B are both happening in the present of my friend's frame of reference. But as we can see, the event A, it's not in the present of the event B for me. Actually, the event A is happening t equal 1, but B it's happening in t equal 2. So I would say that event B is in the future of event A in my frame of reference. So the question now is, which one is the right frame of reference? We have things happening in the present for someone, but they are separated by some time in another frame of reference. Which one should we choose? Now, how can we make a tense logic for this idea of time here? Well, as I said before, to make a tense logic, we need first to choose a set of instants of time that we can call t, and we need to choose also the relation, the precedence relation. We need to tell how these instants of time are related, how they are organized. Well, but can we talk about an order of events or an order of instants of time here in this representation? Well, there is events happening in the past of one observer, but happening in the present of another observer. How can we organize this in a tense logic? There is actually some organization, some kind of order in Minkowski spacetime. There are some events that happens always in the same order for any observer, so for any reference frame. So let's see which events are they. But we're talking about events, and before we were talking about instants of time. Now, instead of calling the elements of this set here, instead of calling it instants, we're going to call them events. And that's because in Minkowski spacetime or in special relativity, we cannot make any difference from time and space. So it's better if we just take both things together, and instead of calling it instants, we're going to call them events. So the elements of this set now in our tense logic are going to call events, but it's the same idea of instants or moments, or it's the same as we were talking before. Now let's try to understand the order that can be found in this mess here. Let's use the same A, B, and C events that we draw before, and let's clear the graphic and only use these events to try to visualize it better. So I have 3 events floating in space right now, and I want to put one observer, one person on each of these 3 events and see how they are seeing each other. So let's draw the first observer. Let me try to draw this straight. Okay. The first observer has this graphic here. So I can say that I have one person or one observer here in the origin of this graphic. Here is the time axis, and here it's the space axis. And he's here, and he is his graphic. So we are still using a Minkowski diagram. So if this guy sent a photon from the origin of this graphic, the trajectory, the path of this photon is going to be the same as we've seen before. So it's going to be exactly like this. And his light cone would be exactly like this. Okay. Imagine now that we have another observer on the point B, on the event B. Let's change the color, and we have his graphic here. I'm not going to draw this big. So his graphic is here, and let's say he also turns on the light. Here is also sent a photon from his point. So the trajectory of the path of the photon would be something like this. Oops. And we also have another guy on the event C, and he also sent a photon from her point of view. So the path of the photon is going to be something like this. So we can have one observer on the top of each event, and all of them are going to have their own light cones. So let's try to understand what we have here. Well, we see that the light the photon that was sent from this guy here on the event A, it can reach the event C. So the event C, it's right on the light cone of the event A. But the event B, it's outside the light cone of the event A. So the event A and the event B, they are not temporally related. But the event A and the event C, they are temporally related. So for events that are temporally related, which means they are inside their light cones, it can have some more, or the order of these events are the same in any reference frame. If we have another event, let's say here, inside the light cone of A, this event, let's call it D, the event A and the event D, which is inside the light cone of A, they are going to happen always in the same order for any observer. So we have 3 kinds of events in special relativity or Minkowski spacetime. The space-like events, which is A and B, they are both space-like events because they occur outside the light cones of each other. We have the time-like events that occur inside the light cone of each other. So event B and C, we can call it time-like events. And event A and event C are light-like events. They occur on each other's light cone. Well, time-like and light-like events occur always in the same order in any reference frame. So let's go back here. As we've seen, event A and event B, they are space-like events, so they are not going to occur in the same order for all observers. In fact, event A is happening in t equal 1 in my reference frame, but it's happening in t equal 0 in the reference frame of my friend. And event B is happening in t equal 2 in my reference frame, but it's happening in t equal 0 in my the reference frame of my friend. So they are both happening in the present of the reference frame of my friend, but they are not happening in the present of my reference frame. They are actually, B is actually in the future of event A. But event B and C right here, they are inside the light cones of each other, as we've seen. Let's say we have the light cone of B here. C is inside the light cone of B. So when we have one event inside the light cone of another, they are always going to happen in the same order for any observer. So B is in the past of C in my reference frame. So B is happening in t equal 2 and C is happening in t equal 3. B precedes C in my reference frame, and is also the case that B precedes C in the reference frame of my friend. B is in t equals 0 and C is in t equal 3 in her reference frame. They are not necessarily occurring in the same time, in the same t equals 0 or in the same t equal 3, but B precedes C in my and in her reference frame. So they occur always in the same order for me and for her, because they are time-like events. Also, light-like events like A and C, they also occur always in the same order. So this is the light cone of A, and as we see, the event C here is occurring right on the light cone of A. So they are light-like events, and they also occur always in the same order for any observer. So C is in the future of A for me and for my friend's reference frame. So these events called time-like and light-like events, we can make a tense logic for them because they happen always in the same order for any observer. If you want to do a tense logic for space-like events like A and B that happens in different orders for different observers, this is going to be a little harder. So we're going to talk only about the events, time-like and light-like events, like events A and C and B and C. The first one to talk about a tense logic for special relativity was actually Arthur Pryor, the same guy who introduced the tense operators and the tense logic in general. So let me clear here. And he says, both theories of relativity admit a local proper time which is linear, and so yields to a tense logic with S4.3 as its Deodoran modal fragment. But there is not just one, but an infinite number of such local proper times. And a distant event B may be earlier than an event A in the frame of reference associated with one such proper time, and later in another. This, however, is only true within limits, and in some cases, an event B is earlier or later than an event A with respect to all reference frames. And so may be said that the absolutely earlier or later, in particular, if the space-time points A and B could conceivably be linked by the path of a light signal, one of them will be absolutely earlier than the other, and the other absolutely later. Well, it is for this public or casual relativistic time that we can construct tense logics with the Deodoran modal fragments mentioned. So he's mentioning a modal logic with tense interpretation, temporal interpretation, that can be used for this kind of events, the time-like and the light-like events that happens always in the same order. And this logic has this frame. So a frame for a tense logic that wants to capture the idea of time of special relativity is a pair T and the precedence relation, where T is a non-empty set of events, instants or moments. We're calling it events, as we said, because it's better to bring the idea that time and space are all together and not separately. And the order of this frame is reflexive, transitive, and directed. Well, maybe what is new here is this frame relation here that says for all instants T1, T2, and T3, if T1 it precedes T2 and T1 precedes T3, then there exists a T4 such that T4 is in the future of T2 and also in the future of T3. Let's try to represent this in a Minkowski diagram. So we have three instances, T1, okay, T1, and we have T2 in the future of T1, so let's write maybe here, we have T2, and we also have T3 in the future of T1, so maybe around here. To say that an event is in the future of another, remember, they must be inside their light cone. So let's draw the light cone of T1 here, right here. So T2 and T3 are both in the future of T1, okay? If T1, T2 is in the future of T1, then there exists a T4 such that T4 is in the future of both here. So there must be a T4 maybe here. That's T4. And that must be in the future of both T3 and T2. Let's see if it's actually in the future of them. So it must be inside their light cone. So here's the light cone of T2, and here is the light cone of T3. And, well, actually, T4 is in the future light cone of both. So it kind of says that all of the light cones, they intersect in the future. I have a better representation here. Let's clean this. So this is a representation of what this frame order says. Here, the points B and C are both within the forward light cones of A. And however distant they are, their own forward light cones will eventually intersect. And there will be points such as D within both, which will therefore be absolutely future of them both. So this is also introduced by Arthur Pryor. And it says that basically all of the future light cones will intersect in the future. And it also is the case for the past, but we're not dealing with the past aspects, but it's an equivalent relation. All of the past light cones intersect. So this is the frame or the semantical way to introduce a tense logic for relativity theory. And we can also have a syntactical way to do this. So we need to choose a set of axioms to represent the facts that this logic is reflexive, transitive, and directed. Pryor also suggested the set of axioms we should have in a tense logic for relativity theory. And he says special relativity tense logic would seem to be obtained by adding to KT these axioms here, axiom 4, T, and G, that he's using this Polish notation. And the system KT is the most simple system of tense logic. It has only these 4 axioms here, and these axioms works for any reference, for any frame we choose. These axioms work, so we call it the minimal tense logic. And we add to this logic these axioms here. We can have the representation in a syntactical way of what we've done in a semantical way. So we said that a tense logic for relativity theory should be transitive, reflexive, and directed, and these are the axioms who represent this. So this axiom G here represents the fact that all of the light cones will intersect some point in the future. We can check this by assuming that this is false in a directed frame and try to find a contradiction. Pryor suggested that these axioms are correct for relativity theory, and the proof that they are actually corrected for the theory were made by Robert Goblat in the 80s. But as we've seen so far, these axioms only cover one part of the relativity theory, the part of the theory where space-like events are not considered. We're only considering the time-like and the light-like events, or the events that happens inside the light cones of each other. And they always happen in the same order for any observer. So there are many other things to be done in tense logic for relativity theory. We would be interesting if we have a tense logic that can deal with the fact that some events occurs in different orders for different observers, or the space-like events. And we barely touched the general relativity. There are also many aspects of general relativity that are different from special relativity. For example, we need to include the fact that gravity also influences in the time dilatation. So there are many things to be done and to be studied in this area, or in areas of tense logic for physical theories in general. It was a lot of information for this video, but I think it shows that physics and logic, they can work very well together. That was a little about tense logic and relativity theory. We only talked about special relativity. We didn't talk about general relativity. So it shows that there is a lot to be done in this area yet. If we want to make a tense logic for general relativity, for example, we would have to consider the fact that the acceleration or the gravity also causes time dilatation, so we would have a different set of axioms. If you want to make a tense logic for the space-like events that are not inside the light cones of each other, we would have something different as well. So there is a broad area to research. Well, finally, thank you again, Maria and Gabriele, for inviting. Thank you for watching the video, and ciao.
Bye.